All right, we'll get started here. Last speaker session of the day. 2 speakers. First one is David Gallaher from National Stone Ice Data Center. I'll be talking about Nimbus project. So this thing actually does work if you want to use it, or you can just use the keyboard. Actually, a laser pointer.
Good. Yep. Oh, good. I like to wander. Well, good afternoon. Here we are. Everybody's had their cookies. The coffee's worn off. You're all going to pass out in the next 10 minutes. So I'll try and not do that to you. So digitizing technology. I said you need to speak on this subject. I'm going, oh really? Okay. Well, I'll come up with something. So, but it is kind of a critical issue. How do you get the data in? Just real briefly, what is the National Snow and Ice Data Center? We're right here in Boulder. We do work mostly for NASA and the NSF. We capture data, we analyze the data, distribute the data, process it. We're now collecting traditional local knowledge and basically education about the cryosphere. So, a little bit about, oh, nice spelling, Dave. First slide, great. Rescue. Jeez, Pete. I love spell checker. It does such a nice job. Embarrasses you all to hell. Yeah. Anyway, I'll talk a little bit about the promise of digitization, a little bit of a couple examples, a ship record example, the Nimbus project, and then some of the pitfalls and kind of what we learned along the way. This image on the right is one of the, this is a 1966 image. It's a infrared image. What's fun about the image is if you look here, you can see a couple of typhoons that are right here, and we actually were able to find the records of the Japanese P2s that flew out to it to actually collect some data. And so you can still collaborate some of this data even 50 years on. So why do this in this group? I think everybody knows why to do it. The Aerial Sea, they've been showing some of this stuff now about the Aerial Sea, and what I find interesting is there's data going all the way back. This is a declassified Argon image from '64. They've now got some videos that are showing that starting around the 1990s, but the data goes back a lot further than that. This one right here is one of my favorites, 1962 composite. So there was global satellite data in the very early 60s. But if you can't tell what changed, how do you tell what's happening? So why do it? Well, the last time we checked, we don't have a decent time machine, regardless of what Hollywood's tried to come up with. But you know, what are the extremes? The time series, the time value of the data. And I can't emphasize this enough. There is now the technology to recover any tape you've got. Any tape, any format. We're working now with several companies. NASA's been working with these guys for years. You can get back any tape, any format. It's running about $30 a tape. So please don't pitch your tapes because you think nobody can read them. These were 50-year-old tapes that were disintegrating, and we were still able to get back 99% of the data. So this is a stat I just was digging around online and found this. If all the spoken language since the beginning of time were digitized, it would consume 5 exabytes of data. In 2007, there were 161 billion exabytes. Email made up 6 figures of that, and I then went and looked, and it's now 10 times bigger than that in 2016. So recovering a little bit of this old data should be really easy, right? I mean, it's a tiny percent of what we're collecting every day now. So what's the promise of doing data? You're saving data. My God, this is great news. You're going to save the data, save the world. You're going to make it discoverable. You're going to be able to do all kinds of great things with it. You're going to find new things that no one expected to find. You'll be able to compare this to other kinds of data. The dark data will be made available. It should be pretty easy just to pull this together and get it to happen, right? So this is an example. I'm not sure anybody's seen this. This came out a little while ago with a couple of really interesting papers, but this is basically the U.S. Mari. This is a Lieutenant Mari who collected data between, I think, 1842 and about 1860, and this was the tracks of every ship. And you can see some really interesting little features here about where they got becalmed in some of the dead zones in the sea. But for the most part, these were where all the whaling ships were going at the time. And you could actually make out the edge of the continents just by virtue of where these ships were going. So lots of traffic going between Europe and the U.S., lots of stuff going around the Cape of Good Hope, tremendous amount of information, of ships going around. But you look at Hawaii right here, pops up quite nicely. And what goes on? This is the modern equivalent of that same record. So how did they do this? How did they capture this data? What they did was they had ship logs and just handwritten ship logs. They then basically abstracted what Lieutenant Mari did was he abstracted that data and said, what's the essential information out of this? And he did this back in the 1840s. Actually went through thousands of ship logs. It was costing about 3 to 5 cents a piece to do them back then, which would be in the millions of dollars today for the total costs. But he picked up thousands upon thousands of ship logs, mostly hiring old ship captains to read these things. And they put the data in nice columnar format, and from that he then produced charts. The charts were so valuable at the time he did this, he was knocking as much as 2 weeks off the voyages because people now actually started to get an idea of where the currents were. So tremendous value out of these logs. Then in the 90s, this data was sent to China, and they basically digitized it and made that data available. So the whole process was a selection, standardization, abstraction, and then make the data available. However, this data is not really an archive of the data. It's just an abstraction of portions of the data. However, it's still highly valuable in this form. So some of the issues with this. When you're looking at the data, is the data a representative sample? Well, a representative sample of what? Every data collection has a bias of some sort or other. The method of how you collected it doesn't matter if it was a sensor. At some point, you're collecting it. I mean, a sensor, I love sensors. But at the end of the day, it's a voltage is all you're really measuring. You're then trying to interpret that voltage to mean something else. And so you inherently put a bias of one sort or another. Any sampling method always has a bias of something. Where did you go collect it? Well, I collected over there. Why over there? Well, it was easier to stand over there than it was over there because that was a deep canyon. I didn't want to collect it there, so I collected it here. What do you, when you're doing this, what's the purpose? If your only purpose is preservation, that's probably not a good enough reason of why to go through these exercises. You have to have a legitimate, hopefully, science or some other reason to do this. What are you hoping to find? What's the logical outcome? If you don't know what you're looking for, how are you going to know when you found it? Will the digital copy really honor the original? This is a constant problem. Is it true to the original? Did you overscan it? Did you capture everything about that original, or is it just a sort of facsimile? Most digitization is an abstraction. You know, what about the metadata? A whole collection of lovely images doesn't do you anything unless you can make it discoverable, and you have to have the metadata to do that. There's always going to be gaps. There's always going to be errors, missing data, lost data, screwed up data, error, you know, these kind of things. How are you going to try and categorize this stuff? The other one that I see all the time is people go to all the trouble. They scan it and then they make it into a JPEG. If it's just text you're trying to capture, that's lovely. But if you're trying to do anything else, if the image itself has values associated with it, if you're looking at temperatures and you make a JPEG, you've in essence lost all the data. You can't use that data as a JPEG. And the other is, of course, it takes a whole lot of massive amounts of cheap labor. So where are you going to get that? So the tools for capturing data, and I just updated this today based on what I found at this conference already. The scanners, we're now seeing 3D scanners, so now you can actually start scanning objects for the first time. Obviously, scanning OCR, we're all comfortable with that. You know, manual key entry. The cursive is getting better, but I still see lots of mistakes in people trying to scan various cursives. Very prone to errors. If you're doing crowdsourcing, there's some nice stuff there, but you've got to look at sometimes double and triple entry to get anything useful out of it. Reprocessing of old tapes, and this is one of my hot buttons. They can all be reprocessed now, even if they're falling apart. The tapes can be baked in ovens now. You want to bake them at 175 until the edges kind of get a little brown around the edge. No, you just bake them at 175 for 10 hours, and you can get the iron ferrite to re-adhere to the acetate layer. Then the tapes can be processed in a one-time only destructive read, but the data can be captured. And this I just heard about is something called the Amazon Mechanical Turk. And I went, what? And this is a marketplace for work. So you can actually take your data, put it up online on this mechanical site, and say, this is what I want done, and get bids for somebody to do the key entry for you. Fascinating idea. I pulled up the website, looked at it. It looks quite good. So scanners, you know, what are you trying to pick up with scanners? What's the size, the resolution, the media, the color, the budget? And for the Nimbus project, we used 3 different scanners. The one over here at the right, one up here, sorry, this is a Kodak HR500. It's designed to handle long reels. You can actually put in whole consoles in this thing. These things were incredibly expensive. I think we spent about $40,000 to buy one of these. I've seen them now come down on eBay to as little as $5,000 to $6,000. They're cantankerous. They only run on, I think, Vista. So you have to deal with it. There's some weird cords and whatnot. Keeping this thing happy and alive is a challenge. We had to tape the cord on the wall at just a certain position. If it dropped a 1/4 inch, it crapped out. Why, we don't know, but you know. We tried replacing the cable several times, didn't help. This scanner right here was $99. And you can see we put a thing so you could just simply reel through this thing to try and get through these tapes. We're actually using that technology right now to scan the ESA data. And I'm not mispronouncing ESA, I'm talking ESA, the precursor to NOAA. And then flatbed scanners, we've built now trays where we can actually put 6 rolls of 35 millimeter film right next to each other and scan them in blocks to try and speed the process up. So you roll in 6 things, turn the crank, roll them all across, and scan another block of them. So this is all data that we've gotten from Jason over at, I still can't say, it's NCDC, I'm never going to get around that. Anyway, but we've been collecting, and so all this technology is being employed right now. And so there are lots of other things, but there is no one scanner that's going to do everything for you, so don't even waste your time trying to figure that one out. So the Nimbus project, I'll just jump into this. This is where we got our teeth kicked in, or cut our teeth, or whatever you want to call it. This was trying to go back and get data from 1964 to 1970. This was classic dark data. When we called up Jason's office and originally and said, gee, I wanted Greenland at the time, and I said I'd like Greenland for 1966, particularly we want the sea ice minimum. So if you could give us September and August, that would be really great. And basically they laughed and said, you can't get it. Look, we have boxes, and in the boxes are canisters. We're not exactly sure what canisters are in which box. But on the boxes, the only thing labeling on the outside is orbit numbers. So if you want that data for that time, the only way you're going to get it is to scan all of it. It was a rather long, pregnant pause on my part. I got back to him, I think it was about 6 months later, and said, okay, send it all to us. And it took us 2.5 years to scan 250,000 images. So the data consisted of high resolution, medium resolution. There was something called the Advanced Videocon Camera System. 1964 was really advanced. But, and then they came up in 1969 with the Image Dissector Camera System, which was a much higher resolution product. Anyway, the data was 50 years old. It was on digital tapes. Cool. So we said, all right, we'll pick up this HIR data and we're going to reprocess that. We found NASA was already working on recovering all the tapes. What all we got to do is just reprocess the tapes. We'll find the ice edges. Project succeeds. So we started down that path. We knew that they had attempted to find some of the ice edges back in the 60s, but with only some limited success because they had nothing to compare it to. Nobody actually knew what the ice extents were back in the 1960s because it had never been measured. So the user documentation, this is one I got a kick out of. The user documentation said the data was so vast, 56 gigs, that no one would ever be able to look at all the data. I've got that in my thumb drive, but just to put it in perspective, I was working for this dumpy little oil company called Exxon back in the 1980s, and we had a 56 gigabyte nearline storage array. It was as long as this room, and it was about 8 feet high, and they had these little robots that run around and grab these 2.5-inch tapes, and you could actually request data and get it in under 5 minutes. That was pretty freaking awesome, and that was the largest storage array on the planet in 1984. Just to put it in perspective. So, could we find the ice edges? So could we extend the climate record is what we were really trying to do to get it back to the 1960s. So Goddard had recovered 4,000 of these 800 BPI tapes. They'd already processed. The company is called JBI, and if you really want to know who they are, please contact me directly because they got into plastics and it's a real pain in the fanny to get a hold of these guys, but I finally got their numbers so you can get a hold of them. This is where we had to bake the tapes in an oven at 175 degrees. They were then read. In the process of reading the tapes, all the tapes were destroyed. They literally took the tapes and just ran it out of the floor into a garbage can. And so it was either you get it or you don't, but they got it. And these were tapes that hadn't been spun in more than 25 years. They've been just sitting on a shelf, and people say, oh, there's no data left on those. Well, yeah, there is. So here's one of the first problems I ran into. Because tapes were pretty expensive in those days, instead of storing the entire record, which was this whole thing, they'd look at space, and they'd have they'd look at the Earth, and then there'd be the housing, and there was a calibration step. They said, we don't need any of that crap. We'll just trim it off and keep just this and throw the rest of it away. So what are you using to trim off? Oh, we're going to use the edge of the atmosphere. So as a spacecraft goes up and sees the limb of the Earth, that's where we're going to chop it off. Well, they used a CDC computer in the 1960s to chop it off. Guess what? It didn't figure out where the edge of the Earth was consistently. So every swath was doing. Okay, and you kind of go, oh, well, we could manually fix those. How many are there? 81 million slices. I don't want that job. So we worked and came up with a solution, and it doesn't show up all that well, but you can see this is Lake Michigan, and it's very nasty looking, and we actually wrote a routine to finally resolve and clean that data up. So great, we've now got a clean data set. We're ready to roll and start looking at the ice. So we lined all the stuff, did the rectifying, the regridding, processed it, and started looking at the ice edge. Then we found out that way too often in the Arctic, the ice and the water are the exact same temperature. We couldn't see the ice. Sometimes you could see the ice, and sometimes you couldn't. And we couldn't tell you when we could or couldn't. So it became a really nice data set, but it completely failed in the objective of determining where the ice was. Actually, a number of people have already used the data now for sea surface temperature. There were algorithms written back in the 70s to calculate this stuff out. But we're kind of going, okay, I've now used about half the budget, and we don't have a solution. So what about the other NIMBUS data? Okay, well, back to those guys over at NCDC. And they said, well, yeah, we've got it. We found out what had happened to the data. They'd collect the data, stuck it in a warehouse that was right next to a bunch of diesel trucks, and it was just vented to the outside, and it just sat there in these boxes for 25 years. Noah was asked, you want this stuff? And I guess they came up to get some other stuff, and they said, oh, okay, fine. And they took it and dragged it down to Asheville, and there it sat for another 25 years. We did ask how many people have actually requested this data, and they said, oh, we've had a few people request it. How many people have ever looked at it? Well, you'll be the first. Because it was classic dark data. There was no way to discover this data, no way to really look at it and get anything meaningful out of it without having to do all of it. You could pull up a frame, that's nice. What are you going to do with a single frame? Plus, the data wasn't, there was no location, it all had to be geo-rectified. The accuracy of the rectification they'd done back in the 60s was good to about 1 degree. So great, we've got the data. Well, first thing was it was film, and we're going, well, why didn't they had the HIR, that was on tape. Why don't they have the why isn't the AVCS on film? They must have lost the film. No, they didn't lose the film. The problem was because of the sheer size of the data, they simply took the data as it came down off the satellite, did a brief recording, played it onto a TV monitor, and then had somebody there with a camera taking pictures of the TV. And whoever they had doing this, we could actually tell when they went to lunch. They'd take pictures, and they'd turn a crank, and take another picture, and turn the crank. And when they come back from lunch, they'd forget where they were. They'd go, did I turn the crank or not? So they turned the crank about 5 times. So there was these weird gaps all over the place when they do this. Unfortunately, this crummy TV camera, or this crummy TV tube, they were still using in 1966, 2 years later. Instead of spending the money to buy a new TV, they kept that crummy TV. Well, it started to develop these lines and crap in it from being an older TV, the way they used to start to degrade in time. And so all the pictures in 1966 look much worse than the ones in 64, simply by virtue of the fact that the TV tube was getting old. But, okay, can we scan all this stuff? Can we determine what is in these things? Can we do the rectification? What's it going to cost? And can we still do it with a remaining budget? So the way we figured out to do it, because the frames were not consistent, they just appeared wherever on the film. Sometimes you get a frame, you get an image. There may not be one for another foot. Sometimes there may be one within 2 inches. So anything to try and detect where the edge of the frame was wouldn't work. We went to NORAD, and NORAD still had the ephemeris data from 1964. This is the orbital data. We said, look, there's a timestamp on the bottom of each frame, and there's the ephemeris data, which says where the spacecraft was at a certain point. So if we could tie those two back together, we know what the spacecraft was looking at. Should be really good, except the timestamps at the bottom of the frame were cut off about 40% of the time where you couldn't read the timestamp. But we knew they were 91 seconds apart, so in one orbit, if we could get just one, we might be able to do something. So we also had to center each image and then try to guess those times. So if we get one good time, we could then navigate it, and it would plot for the student where the image was. And they could say, does this actually make sense? Do you see this feature? If this is where the image is supposed to be, and it's not over the middle of the ocean, you should be seeing this feature. So we had a way to check the data. So students sat there and started this thing. We were really worried about their sanity, sitting in front of these screens for whatever. Some of them have actually gotten out now, so they're doing better. But lots and lots of film, lots and lots of time. About 4% of the data we couldn't use because the images were such low quality or just plain bad. This is one that really bit us. We're marching away through things. Things are working great. And if you look here, we scanned, every image had a grayscale up at the top, which NASA was good enough to do back in the 60s, thinking ahead. So we said, I think we're seeing some stuff here that just doesn't look right. What was happening is our scanner, with its advanced technology, was making every image look pretty. It was automatically balancing the images for us. So it would make just a nice level of gray, nice level of black. So it meant that the grayscale was not consistent. And they quit making these machines in 2002, so we had to dig around, find an engineer how to turn the damn thing off so it would stop making the images pretty and record what was really there. So be careful when you're scanning. What you think you're getting may not be what you're getting. You may have to go scan so we would go back and rescan images every now and then to make sure the thing hadn't drifted off. So, like I say, these lines, these should have all been absolutely coincident, and they're not. That was the problem. So we were getting different grayscales, and if you're dealing with new imagery that doesn't have grayscales, you're going to have to come up with a new technique of how to figure that out to know that you're actually getting what you think you're getting. How well does it honor the original? So this gives you an idea of what we were running into. So we wrote software that would treat this like a video game where the students would come through, and you can see only parts of the dates were showing up, so we digitize these little bits of the timestamp at the bottom, and the computer would try to guess which one it was, and the students would then go through and validate and say, yeah, that's the right one. Then they'd tag the center, they'd scan the image, and it would give them a little plot to say where the image was, all in real time. So this gives you a little idea of what those nimbus look like. This was actually the first image ever taken by Nimbus. It's 1964, and you can see some of the ice. In fact, the first images of Europe ever taken from space were taken by Nimbus. And here you can see some of Baffin Island, again, 66. Some of the things that were really nice was this, you can't really, this doesn't do it justice. What they had was, all that was available was these old APT, and these were automatic picture transmissions. These were printed on old facsimile paper. And this image is the image we were able to recover, and there's just so much more detail you can now see in this than what you could see there. So the data has been heavily used. Actually, at NSIDC for a time there, this was our most popular data set. Comparing the imagery, this is a fascinating one. If you look, this is Independence Glacier, 1964. Here it is 50 years later. You're going to go, well, gee, look at the ice age. We called this the rhino head. You see this little bump right here, a little face, and there he is right there. Same bump, same face. What's changed is this is about 70 kilometers from here to here. Solid ice in 64. Now it's completely, the glaciers are gone. And this is northernmost Greenland. Fairly remarkable change. We did see some change right in here. This thing is starting to open up a little more in here where the ice sheet itself is starting to melt. Okay, so great, we want an ice edge. How do you do that? So we did what's called compositing. We simply stack the images. The idea is that clouds move when ice doesn't, at least not as fast. And you can get a thing like this. So here's a look at, this is looking in 1970, and here you're seeing the ice cap in 1970. Here's the Antarctic. This is also 1970. But you can pretty clearly see by stacking these hundreds of images together over about a 7-day period, you can see cracks, you can see quite a lot of detail of the ice from this image. We were able to then use this to calculate what the ice extent was back in the 60s, and we got a lot more variability than we expected. That's the subject of several papers. But what you end up with is a really nice ice extent over time. And so you really start to get an idea of what's going on, and there's a major transition here basically happening in that 1970s period where the ice was actually quite a bit bigger in the 70s and 60s, and it dropped off. So the Antarctic may have actually seen evidence of it dropping off much earlier than the Arctic did. So, pitfalls, digitization. It's slow, it's expensive. What else can you say? The media is frail. It falls apart when you try to look at it, trying to get students to touch it. How dark is your data really? How complete? As usual, as has been talked here before, the funding is always a joy. Trying to pitch this to agencies to say, we can actually do something really valuable. They didn't care anything about recovering the data. They did care about getting some new science out of it, and that's what sold the project. So you have to make sure you've got a real science objective before you start this thing. You'll get traction with that. What else should we have done? What else could we have asked? Who could use this data? Was there any real documentation? One of my favorites was, is anybody still alive who can talk to us about this? One of the guys I ended up talking to was with, he would only talk to me if I said I was a member of a credit union, because he left NASA and became president of the NASA credit union, and turned to be a huge source of data. The rest of this, is it consistent? Can you really get the scanner to do what you want? How are you going to put it all together? That sort of thing. So why do it? Obviously, if you can't tell, if you don't know where you've been, how are you going to tell where you're going? Don't forget, by the way, publicize a successful project. That gets more funding for everybody else. And just for the record, we're also now going after the ESSA data on a very, again, shoestring budget, and we're recovering that data from 66 to 72. Continuous coverage. So, thanks.
Yeah, so if I'm interested in the position of the Gulf Stream, will these data help me? What's the accuracy, the spatial accuracy
The
of
spatial
your...
accuracy was about 7 kilometers. The temperature accuracy is about 1 degree.
Yeah, that would be easy for the Gulf Stream.
Yeah.
And spatial, so you know where the center of the pixel is to within 7 kilometers.
Right. So it's nice, a nice data set. And they did back in the 70s. You can find papers of how to calibrate the data for the infrared, deal with the atmospherics and all the rest.
Yeah, I don't care about that. I just want the position. And and you have 2 fields a day, nighttime and daytime,
Yes.
from when to when?
64, a few months of 64, a few months of 66, about half a year of 69, and 1970, 71.
And you're now going...
Now we're going back and getting the ESA data. The ESA data, though, didn't have an infrared sensor on it. Or it did, but it was really, really crap. Any other questions?
Thank you for your talk. Just really interesting and such a broad picture. And your comment about publicizing successes is very important. So I just have sort of a comment that's been on my mind. This word dark data, it doesn't have a positive meaning, even though to us, we want to sort of discover it. And so I just like dark web, you know, has kind of very negative connotations. I don't know if people are familiar. So I of course, Wikipedia, just looked it up, and it's you know, things that aren't so hot, like guns, chat, abuse, porn, hosting, hacking, and, you know, counterfeit, whistleblowing, and so forth. And if you look up meanings of dark data out there in sort of the popular world, it's not so positive either. Even though our notion of dark data existed before probably the web. And I don't have an answer, but since we keep bringing it up, I just wanted to get it out there, and I don't know how it fits into our dialogues. I'm kind of a metadata person, so I think about the semantics and the message we're trying to convey. And
You call it not bright data, but I don't know how that works.
you know, so of course I'm sitting here and I'm looking up gray data, maybe, you know, but you know, I don't have an answer. I just wanted to bring it up, and I'm thinking about it.
So, Dave, my question is that many of the high-profile data rescue projects, the Nimbus one and the lunar rescue work, which we discussed in the session, and the work that Elizabeth herself was involved for the ozone-related data, and there may be others that I'm missing, all are some way or the other related to something that you alluded in your talk, to certain important scientific activities that are either currently taking place or are in the central theme of the work that's going on. So the question I have is that data rescue of, let me be a little more myopic, data rescue of scientific records or will be mainly have success if they are aligned towards such contemporary, new, high-profile activities, missions that are going on some way, so that the collective collation of the data will provide new meaning, or it can be more on a generic social, when I use the word social, at a smaller investigator level where experimental work is going on and it's not tied to any major mission.
Well, I guess what's the question?
The question is the data rescue activity going to be primarily more funded, or will have more success if they are aligned towards such activities, such as major scientific activities ongoing, be it satellite observations or ozone research or any other ice, snow and
You'll
ice?
have much more success if you can tie
I'm
it
sorry?
to some. You'll have much more success in getting the funding if you can tie it to something of what you're hoping to find that's actually answering a fundamental question that you can go back in time to answer. that's where you're going to get your funding. If you're simply saying, I'm going to recover the data for the sake of recovering the data, you'll get no traction.
So from identifying different data sets, do you think that the best way to go about is first starting off with these kind of activities more, or widening your sphere?
I think it just depends on the data. If that data can actually answer something, it may be a small, very localized data set, a particular study, but if it can answer a question that couldn't be answered before, I think they're going to look.
Okay, I'll leave it there, because you use the word dark data, and if we don't know whole about the data, then how would we define a question?
That's where the fun starts.
All right, thank you, David. Okay, so we have our last talk of the day, and then we'll have one more breakout. Janine.
All right, so I thought we had a microphone up here, or no? Oh, this one, perfect. Oh, this is even better. I didn't even see this one. That's even easier. Okay, perfect. That way I can wander around and not make it too quiet. So you guys hear me all right? I tend to speak quieter than I should in big auditoriums. So I'm going to talk about a project we did this last summer. It has roots going back longer than that, but we had the opportunity to hire a summer intern, and he, in the interview process, was really excited about going in and doing the technical work required to recover this data. So he's got first authorship on this, and this is all work he did this summer with my oversight and guidance, and a lot of other people helped too. At in-car here, we've got our modern aircraft that Mike Daniels talked about first thing this morning, the C-130 and the G5, but we've had aircraft collecting data going back to the 1960s, so I've got a list of them there, and we've gone through a variety of formats we've stored that in. We currently store our data in NetCDF, and the last talk actually cracked me up because our data system that does that is called Nimbus, something totally different than the Nimbus they were talking about. But before that, we had a GenPro 2 format, and before that a GenPro 1 format. And back in 2011, we got the GenPro 2 data converted to NetCDF, but GenPro 1 provided kind of a bigger challenge because we really didn't have much in the way of concrete documentation. We had information on the system that collected the data and kind of the software that for that side of it, but we didn't have any information on the data format. So the first thing we did was we had the data, we got it into our archive back in 2014 just to make it accessible that way. It's been available online, but nobody's used it because what would you do with a compacted binary file? We've located all the sources of documentation. We found all the people we could find who were around back then. But we never found a description of the actual binary format. So we said, okay, we're going to have to take these we have chunks of code. None of them run. None of them are complete. They were used for all kinds of different processes. Let's see if we can reverse engineer these things and come up with the format of this data and then convert it to NetCDF. And our student got all excited about this. And then, you know, hurrah, we're going to have data that people can do research with. It's going to be wonderful. But that was our process. So, looking through everything, our software and hardware are no longer available, like I said. We had some printouts. That ended up to be really, really helpful, but nothing in digital form. Pieces that we did have were just a mess. So, went through this process, and I know that this is not a very technical audience, and I'm going to try to keep the technical to a minimum, but I'm a software engineer, so I have to go down that path a little bit. So computers store stuff in ones and zeros. When I say it's a compacted binary file, it's a bunch of ones and zeros. We didn't have as much space back then on computers, so we tried to really compress everything in the best way we could. You could store things in base 8, base 16, ASCII that we all think of. The text really wasn't always a standard. There were weird ways of storing stuff back then. So we had to do a lot of detective work. First thing we did is we did a dump of our file. From looking through our documentation, we said, oh, there's going to be a header at the beginning of this file. So if you look at this, I'm doing this right. I'm sorry, I'm moving the slide, not. Oh, I see. Ah, okay, awesome, thank you. Okay, so this is just the binary representation of the data in octal, so it gives you, it goes up actually through F, but they're just characters. This is turning it into ASCII. And we said, well, this is supposed to be a header. This looks like junk, right? So that can't possibly be what we need. But looking through the documentation, we found out that instead of using 8 bits, they were compressing it as 6 bits. Oops. So maybe that has something to do with it. Then we also found this little chunk of code that's just an array. It's got all these numbers in it. And we started doing some more reading and figuring out, and we figured out that, okay, we can assign 6-bit ASCII values to these. And when we do that, and this is some of the code that we saw that kind of gave us that 6 that tells us it's the data bit and how things are mapped. And we said, okay, this looks like we might be getting somewhere. And sure enough, we came up with this table where we could map the values we were seeing in the files to ASCII. And we found out online that that table existed online. So we were actually doing something that other people had done, and that really seemed to be on the right track. So we were thrilled all the people had given us these clues in the code and said, okay, let's see if we can decode this. So we have that table. Here's a little chunk of data. Let's apply the table. Okay, so we've got the original values. We convert it to binary. We apply that 6-bit decimal change. We convert it to ASCII, and lo and behold, we found a phoenix. So we're like, hurrah, that's actually a real word. We think we found something. It's actually not the phoenix I have there. It's this phoenix, which was a project we had back in 1978. So, and we thought this data was from the Phoenix project in 78, so we're starting to feel pretty good about all this. So this is just a little representation about what I was talking about the 6 bits. So you have 6 ones and zeros, and you really need 8. To read it in modern stuff, so we had to unpack that and add that spacing. So we're getting letters, but we don't know how far to go into the field. We're starting to find a header. So let's just start going from bit number 1 and see what we get. And we just worked our way through, and we came up with this header with all kinds of information in it. The most interesting part of this, or useful for us, was the numbers, right? So we start to figure out, okay, there's 67 parameters in this file. Things are scaled to 20-bit integers and packed 3 samples per word into 60-bit words. So, okay, this is information that as software engineers we can actually use to decode this data. And so that's just showing it that there's parameters. The first parameter is time. Then we have a unaltered tape time, a time lag. So, and going into actual physical parameters about the atmosphere, like temperature. And it seems like everything's ordered sequentially. We would hope so. That's kind of the way the human brain works. So we'll try that. But we need to figure out what these chunks of data are and what the separation between them is. So we started doing some math. That red box is supposed to be around the time, but that's okay. So the first parameter is time, second since midnight. And from our previous documentation, which we got from another source, we know for this file that this time, the start time of this file was 8:38:31. So we can convert that back to 16-bit, and then we can just do a grep, dump our file and grep it and find that string of numbers and figure out where we are in the file. So the offset that I've circled down there is kind of what bit we're at in the file. Find the next 1 second later, find where that is, and get a sense of how big our chunks of data are, our records are. So here's a bunch of math. I won't go through it all. We can check it, but kind of working at it backwards. And we start finding that we've got some information now to start decoding the data. But as soon as we go to the second file, we find out that the chunks are not the same size. First one had these 409-bit chunks. The next were 466. And as we went through, we found out that there were lots of different variations on this. 819 records had the same, but then it just gets crazier from there. And machine reading was a new thing back then, so people weren't that consistent in what they did. They were assuming a human component. So that was a big hurdle for us to overcome. Here's another example of it. That header, if it were machine readable, it'd be nice in columns, but some of the columns were kind of all over the place. The spacing wasn't quite right, so we had to write code to deal with that. Everything was blocked. So if you're going to compress all your data into this 6-bit compressed binary thing, how do you know when it starts and ends? Well, people were pretty clever. You put a little defined 8-bit thing at the beginning that says you're now going to see 763 bits of data, and then at the end you say you just saw 763 bits of data, and then you put a new number in, you're going to see 312, and then you just saw. So this blocking helps us to split the data up into chunks on different tapes to keep track of it. It doesn't tell us what the format is inside of that. That was the original work, but we also have to get rid of that blocking. 2 kinds for this data. One called coast blocking is something that's been around at NCAR for quite a while, and the utilities actually still exist and still work. That was easy, woohoo. Something not so easy was that NCAR had a terabit memory system that had a different type of blocking, and that software was not currently available, and the documentation wasn't everything we would have hoped it would have been, although there was a technical note, so it was much better than where we were for the GenPro. So we took this technical note, dug through it, looked at all the documentation, figured out what that format was, and had to write code doing the same process that we did for the GenPro one, like, chunk through a little bit, find something out, do some more, iterate back and around. And so we've got this going, and now we can get the chunk, the blocking off of our files, iterate, get our data. But because of things like those columns not lining up or other different things, it doesn't always work. So our process was to run our script, get a bunch of errors, try to catch all of our errors, grep through them all, look for all the errors, figure out what we can do, fix some of them, run again, do it again, do it again. And this picture on the bottom right is actually the student's notebook. He was great. He took very meticulous, really neat, nice notes on everything he went through. And so we started coming up with lots and lots of use cases, right? For this flight, for that Phoenix, we have this one issue. For this other one, we have this other issue. And pretty soon your code and your process is going to be a big mess. So we decided that we needed to kind of separate that from the main part of the code that does the processing. So we made these like rules framework chunks of code that let us keep it clean and say, for Phoenix, we found the following problems and this is how we're going to fix them. And for something else, we found the following project problems and this is how we're going to fix them. So that's just a sample of that little chunk of code. And that's been really good. That's allowed us to kind of keep track of it all, keep it clean. So lots and lots of rules, lots and lots of little subroutines to deal with those rules. And then, as we've talked about here before, document it and distribute it. So we got a workflow going because guaranteed there will be problems. We will convert this data. I will check it. We will see if we think it's good. But somebody in the future is going to say, wait a minute, that doesn't look like temperature. That was offset. Something was wrong. We need to do this again. So we want a good workflow document. We have all of the all of the software online in GitHub. That's publicly available, so if anybody else has GenPro 1 data or if they need to redo this, they should be able to access it. And so here's our lessons. Don't be afraid to explore, use lots of different tools, check lots of different things, change your direction, develop as many tools as you think are going to be useful. We had quite a few that were just for trying to decode what this is and learn something in our process. Take lots of good notes. And then make your results available. Publicize it so other people can get funded, as the last speaker said. So here's our quick results. We were able to recover 72 data sets from 59 projects from 1975 to 1983. This encompassed 1,162 flights. We had some missing that were reported in our old documentation. It turns out we actually found more, so things we thought were missing weren't. So we were able to recover 8 files we didn't know we had. We converted all these files, and we had about a 78% success rate, or if you don't include the ones that we expected to be missing, an 87% success rate so far. We hope to increase this, but already that's pretty good. Of the data we've converted, that's the coverage on the globe that we have, so that we now have data in those areas in the pink from those time periods. So that's pretty cool, obviously centered in the US, but there were also some international projects that happened. We're hoping this will be good for climatology and for comparing with the data we have now and be good for people. So thanks to lots of people. Just since he's here in the audience, I'll point out that Mike Daniels was actually a student working with this data way back. So he ended up to be a great resource for us. And That was good. Yeah, and so lots and lots of people we had to bug to get help with this stuff, and it was a fun project. Hopefully I didn't bore you too much with the data, but gave you a little sense of how computers work and how things used to be done. And if you've got a big project like this, you'll have a sense maybe of how to look at it. Thank you.
Wonderful presentation, really cool stuff. I was wondering, could you give us a rough idea about how many person hours of analysis and programming went into that?
Student was actually quite a hot shot in the, computer digital binary stuff. He was really excited about the project and really worked hard. But we had him only for about 10 weeks this summer to get this far. So full-time for 10 weeks, minus, as an intern, we have intern programs where they go to talks or do different things. So it wasn't exactly 40 hours, probably 35. So maybe 350 hours. And we're not completely done. All the 85% is converted, but I still need to do some checking and verifying of it, and then we'll have to probably do some reprocessing of certain things. But we have a real workable thing that he was able to develop in that short time.
Great work.
Yeah.
If you weren't able to find those snippets of documentation from the original project, do you think it would it have been possible at all, or taken 5 times longer, or
I think, yeah, it could have taken a lot longer. That clue that things were packed into 6 bits instead of 8 like we expect now was huge. If we hadn't have known that, I guess you could have gone through other documents to see what was generally done in that time frame and maybe figured it out.
Right. Documentation is pretty key, I guess.
Yeah, that's why I say thanks to those people for holding on to that, because even without a document that described the exact format, that was huge for us, yeah.
So I also have a documentation comment and question. Comment is this, or maybe it's a question too. So you're publishing this tech note also as an NCAR tech note?
We hadn't gotten that far.
All right.
Possibly, yeah.
Well, as a member of the NCAR library, I encourage and
Yeah,
recommend that you do so.
Yeah. I think considering that the software is online, that would be great. Instead of, I think right now the documentation is up in GitHub with the software, but it'd be much more visible as a tech note. So yeah, we should definitely consider that.
And then my question is about, again, the documentation that you were looking at. Was it generally, were they published documents like the NCAR tech note, or were they, sort of where did you get this documentation? Or was it, Mike, did Mike have it in his his basement?
Mike had some in his head. What we had at RAF, the Research Aviation Facility, which is the group within NCAR that hosts the aircraft, was 3-inch binders with printouts of all kinds of stuff and multiple copies of them, but I didn't ever find them through the NCAR library, and so I have actually sent all those up to our new archivist who is here, and she's going to get all those online for future people to be able to see. Those documents, though, tended to be more about the software that created these files as opposed to software to read the files or the format that they were created in. So I assume at some point that was documented, but we never found it. But yeah, hopefully all that stuff will be online, and this will be something that other institutions did save stuff in this format, and so if they've got old data, they'll be able to use this as a starting point and have an easier path. Yeah.
Working with easy data is no fun. Working with this harder stuff is more of a challenge. Do you have a list of questions that you went through that could be documented and shared, or is that on GitHub? Like checking the format: is it 8-bit? Is it 16? Is it hex? Is it this? Is it high byte, low byte? Are the first 2 numbers an ID? Do you have a whole series of things that if someone else is given, a pile of binary data that they could use as a starting point?
Yeah, so within the workflow is some of that, but a lot of it is really documented within this talk. And actually, as the end of the summer internship, he gave a talk that had much more of the technical detail that I have that we want to archive as well. That I tried to not overbore people who aren't into the bits and bytes of data and computers here, and just kind of give a high-level overview. But we have that more details, and that really ought to be, documented and saved in a better way. it was very much a evolving process. When I started this process, well before the student came along, I thought, well, we're going to have snippets of code around. We're going to have a document what the format is. I just have to find it. And it took a while to realize we don't. We're going to need to get somebody who's excited enough about digging into this to really reverse engineer it. So yeah,